Is dark matter the gravitational shadow of some parallel universe? One of the known stuffs which we can't see or touch is dark matter. We know it exists because it affects the motion of regular matter, which we can see. It's been around 100 years since we have been able to vaguely predict such kind of matter. However, it wasn't until the 1970s when certain data proved through the movements of stars and galaxies on the presence of way too much mass that we were able to observe them. Interestingly, dark matter's gravitational field influences where the biggest concentration of matter ends up. So, galaxies and galaxy clusters' defined position is due to dark matter itself. One of the predictions of string theory is that our universe is a sheet of spacetime, which is termed as brane, floating in a higher dimensional space called bulk. Our universe might get overlapped with other branes, which may be a small distance away from us. If this is right, then it turns to be true to say that what we perceive as dark matter is residual gravitation from matter in another universe. It's just because of this, we don't see it, and it simply doesn't bump into things. The problem with this kind of visualization is that to prove it right would require multiple steps beyond the fangs of direct experimental evidence. So far, none of the experiments has validated the evidence of branes, bulk, and string theory itself. These are fascinating ideas, but are yet to be proven. Before diving into the bulk and brane stuff, it's worthy to consider what we know on dark matter. By precisely collecting statistical data on the number of stardust, stars, and their distribution of masses, and then calculating the amount of gravity due on all of it, we can get to know how fast each star in the galaxy should be orbiting around its center of galaxy. Interestingly, we found there's many times more matter than we can see. Furthermore, these unseen matter exist in each and every galaxy. When we compare seeds of stars with the distance to their galaxy's cores, we find that they are orbiting a disk of stuff which is metric times more than the predicted mass. Hence, there are many dark matter, and interestingly, they don't bump into anything. The difference between the 70s and now is that our computing power and space telescopes have advanced big time. So, we have been able to validate that dark matter exists, and we also know where it exists and how much is around. Gravitational lensing bends light as it passes really heavy objects. By determining the degree of distortion, we can calculate the amount of mass the object has. This would have been very difficult without computing power. If regular matter and dark matter show up in more or less the same place, then it is hard to tell the difference between the misunderstandings of how gravity works with the existence of dark matter. Fortunately, dark matter weakly interacts and is also heavy. Due to this property, it reveals itself when huge blobs of ordinary matter collide, while their associated blobs of dark matter notably don't. The bullet cluster, 1E0657558, consists of two colliding clusters of galaxies. Gravitational lensing studies on bullet clusters provide the best evidence till date on the existence of dark matter. When galaxy clusters collide, their stars miss each other, but their massive gas clouds find each other in the course of this massive galactic collision. Due to this, they heat up until they glow in the X-ray spectrum. These impacts stand out clearly as they are in X-ray spectrum. When galaxy clusters run into each other, there should be a decent smearing of mass with a big chunk in the middle where the gas clouds flatten into each other. However, instead, what we observe is that hot gases in the middle of the impact collide, with the most mass taking the form of the huge chunks that cruised right through. Hence, dark matter exists. It is not just a mistake, or miscalculation. You can certainly point at where it is, predict how much is there, and even talk about what they are doing. The problem is we can't touch it and feel how it is, as it can't be detected directly. Different particles interact with the presence of different forces. There are 4 fundamental forces that exist in nature, namely 1. Strong nuclear force, 2. Weak nuclear force, 3. Electromagnetic force, and 4. Gravitational force. Protons interact with all these forces. The strong force binds neutrons and protons tightly together in atomic nuclei. Electrons, on the other hand, do not interact with strong forces, although they interact with the other 3 forces. Neutrinos only interact through gravitational and weak forces. Without the electromagnetic force, neutrinos are free to pass through any damn thing near you. 1 trillion neutrinos can pass through an object per second, but only dozens of neutrinos can be detected by our best, biggest neutrino detectors. Since neutrinos interact with weak forces, neutrinos are also weakly interacting. Dark matter does not directly interact with electromagnetic force, so it passes through ordinary matter and itself. It just interacts with gravitational force mainly on large scales. It wouldn't form any elements, as it doesn't interact with strong nuclear force. Moreover, it doesn't interact with weak nuclear force, so we're left with no way to detect it directly. So the only way out is to detect its gravity. To answer the question, could dark matter be the gravity of stuff from another universe? The answer is, well, probably not. Dark matter doesn't interact with ordinary matter, which could be because it's on a different brane. We now know how it's been distributed, and how it doesn't interact with itself either. Bringing an extra universe into play doesn't answer any question. It just complicates the existing question with untested ideas. If you've liked Inkstall's edutainment, then go to inkstall.in and sign up for free. Producing our videos takes a lot of time. If you'd like to support Inkstall, you can do so on patreon.com/Inkstall. Please refer the link below to buy Inkstall's book on space, time, and beyond.